Hello everyone. So in this lecture we will start discussing neural language model. Okay. So in the last class we have completed word embedding where we talked about glove, and before that we also discussed word to vec and count based methods. We will see how these methods are used in neural language model. Okay, for this chapter these are the prerequisites. You should know what is a loss function, how backpropagation happens, right? You should have a fair bit of understanding about CNN and a little bit of understanding about RNN also. Okay, so let's get started. This is a neural language model. We already discussed statistical language model. If you remember, the task was to predict the next word, right? This was the example that was shown. I like pizza with lots of dash, right? And the language model should be able to predict the appropriate word, right? And how the language model predicts, it basically samples a word from a distribution. What is the distribution? It depends on the hypothesis. Let's say if you are designing a unigram language model, so distribution is sampled from a unigram model, otherwise bigram or trigram and so on and so forth, right? What are the major problems in statistical language model? The major problem is that for an unknown word, it would be very difficult to process it. The bigram matrix that you compute would also be sparse, right? And so on and so forth. So now we move to a neural language model. It was proposed by Yoshio Bengio in 2001, 2002 during that time. Not exactly the one that I'm describing here, but somewhat similar to what we will discuss here. Okay, so we'll start with a CNN method and we'll see that how a CNN method, a CNN model predicts the next word. Okay, so for a CNN method, we all know that when we run a CNN on an image, right, let's say an RGB kind of image, what we do, we identify a particular patch, right? Let's say this is an image, right? We first identify a particular patch, and on top of this patch we apply a kernel or a filter, right? What is this kernel or filter? This is essentially a matrix W, which is same as the size of this patch, right? We apply this here, and then we can use, let's say, max pooling, min pooling, etc., right? These are, you can also think of some non-linear function, right, out of whatever you got, right, from this kernel. So you need to first identify a patch size, right, a window size. Here, in our case, in case of language or a sentence, a sentence is a sequence of tokens, right? So I also need to identify a context or whatever, a patch size here also. It's a 1D matrix. It's not a 2D matrix. It's a 1D matrix where there's a row, and in that row the tokens are arranged, right? And these tokens are essentially represented by word embeddings. Okay, so to use a CNN, what we need to first identify a window size or a filter size, a kernel size. We can't process the entire sequence at one go, right? So let's say this is the sentence. As the proctor started the clock, the students opened their dash, and you want to identify the next word, right? And let's say the size of this window is 4, or size of this kernel is 4, right? So you look at the previous 4 words and you discard all these other words. Okay, so you discard them. Okay, so this is now the patch that we are focusing on. Okay, now we apply a CNN kind of layer on top of this. So the is represented by this vector x1, this is x2, x3 and x4. x1, x2, x3, x4 are word embedding vectors obtained from, let's say, word to vec or glove, or it can be as simple as one hot encoding, right? Then let's say the size of the vector is 4. So 4, 4, 4 and 4. So it's a 1 cross 16 matrix, right? And on top of this, I apply the kernel or a filter W. W is a matrix, right? When I apply this, let's say the size of this matrix is 16 cross 8, for example. right? When you multiply this, it will produce a vector size of 1 cross 8 or whatever, 18 transpose. You just look at the dimension. Okay, so it will produce another vector of size 8. Yes or no? Right? So now this is my hidden state. What is the goal? The goal is to predict what is going to be the next word. And how many words are possible? How many candidate words are possible? Vocabulary size. Let's say there are n number of let's say n is 1 million. So there are 1 million number of words present. Any of these words can basically come here. So from this hidden layer, right, what I do, I apply another linear layer. Linear layer is just a feed forward layer, right, which will basically up project, right, this 8 size vector to a million size vector, right? So what is the dimension of this U? 8 cross 1 million. It's just an example, by the way. Okay, so it will produce a vector of size 1 million, and of course after this projection you apply softmax and all this stuff, so that the entries of this vector will be basically probabilities, and all the probability laws will be followed. Okay, so I will get the distribution like this. From that distribution I will sample, and hope is that the word with maximum probability will be sampled. So this word can be either books or laptops, for example. This is CNN. Clear? So you flatten the entire matrix, you apply CNN layers. You can have multiple such layers, by the way. There's only one layer I showed. You can have multiple such layers. Okay, and then you sample it. What is the problem in this kind of approaches? The first problem is that we have to decide the window size, right? We can't consider the entire context as a window. The second problem is that the size of the window, which is 4 in this case, is an hyperparameter. Meaning you have to play around this, you have to play with multiple values of this window, and you have to see which one is better. So as we increase the size of the window, the dimension of W will change. It will also increase. So with the increasing size of context, with the increasing size of window, the dimension of the weight matrix that we are going to learn will also increase, right? These are the two major problems. But what are the good part about this CNN method over statistical language model? What do you think? Do you think the sparsity can be addressed here? There will be no zero, right? It can also handle unknown words in a very systematic way, right? Assuming that the word embeddings are available, otherwise you can use one-hot encoding and so on. So these are the good parts. You don't need to store this entire matrix, by the way. You don't need to store the entire bigram matrix here. Okay. The other problem, the problem that I mentioned, the first problem is that you need to decide the size of the window, right? With the increasing window size, W will increase. The third problem is more subtle. Let us discuss the third problem. What is this third problem? The third problem is that, let's say you have this W matrix, right, which is a 4 cross 4 matrix. Let's say a 4 cross 4, right? Let's say 4 3 1 5 7 4 3 2 1 2 7 5 1 1 2 5. This is the W matrix. Okay, and let's say this is my embedding. This is the embedding matrix which will be multiplied with W, right? And let's say the embedding matrix is like this: E1, E2, E3, E4. Let's say E1 is the embedding for the word da, and E2 is the embedding for the word students, and so on and so forth. This is a 4 cross 1. You have to multiply these two, right? And let's assume that these embeddings are one-dimensional embeddings, just for the sake of discussion. Okay, if you multiply, what is going to happen? 4E1 plus 7E2 plus 1E3 plus 1E4, right? 3E1 plus 4E2 plus 2E3 plus 1 E4, right? 1 E1 plus 3 E2 plus 7 E3 plus 2 E4. So what is actually happening? You notice what is happening here? E1 is only affecting this column. E2 is only affecting this column. E3 is affecting this column and E4 is affecting this column. Okay? So ideally, when we do this kind of multiplication, right, weight and embeddings and so on and so forth, we hope that it should not be disjoint, something like this, right? The hope is that when we multiply, the information from E1 should pass through all the columns of weights. The information of W2 should E2 should also pass through all the columns of the weights, and so on and so forth. Now, I mean, when I multiply something with something, what I'm doing essentially, I'm essentially doing some sort of message passing, right? But here, if you look at it carefully, E1 is not affecting column 2, E2 is not affecting column 3 and column 1 and so on and so forth. So essentially, the message passing is not actually happening at all. You are essentially learning 4 independent functions, right? It's a very subtle, think about it carefully. It's not very easy to understand, right? You pause and ponder and then maybe we'll discuss again. So there are 3 problems. The first problem is that it depends on the fixed window size, right? It is not able to capture infinite length window, right? The second problem is that there is no message passing happening, right? And the third problem is that with the increasing size of window, right, W is also increasing. So let us address this using RNN, right? What is an RNN? So an RNN looks like this. So let's say I have inputs x1, x2, x3 and x4. These are embeddings, right? These are embeddings, and we have different hidden states. So at every position we have a hidden state. So it is position 1, position 2, position 3, position 4. You can also think of these positions as times. Time 1, time 2, time 3, time 4, right? And this is hidden state 1, hidden state 2, hidden state 3, hidden state 4. And let's say there is a dummy hidden state H0. Let's start with. Okay? And how we are computing every hidden state? Every hidden state is computed in this way. Let's say H1 is computed. So there is a weight parameter matrix WH here, right? There is so this parameter matrix is essentially a projection, a parameter matrix, right? And you have another parameter matrix WE, for example, here. So H0 will be multiplied with WH, right? X1 will be multiplied with WE. This will be added, of course, some bias term, right? Okay, and then I will pass it through a nonlinearity. This will be multiplied with this. This will be multiplied with this. We'll add them, add a bias, and we'll basically pass it through some nonlinearity, sigmoid or tan H, right? That will give you the hidden state. So now, look at here. H1 is determined by H0 and X1. H2 is determined by H1 and X2. H3 is determined by H2 and X3, and so on and so forth. So essentially HT is determined by HT minus 1 WH plus XT WE plus a bias B, right? If you look at it very carefully, this is a recurrent function, right? And these 2 weight matrices WH and WE, they are the same across all the layers. So here there are 4 layers, right? So they are the same across all the layers. And these matrices WH and WE, they are independent of the context size. There is no concept of context at all. But if you still want to consider the context, it is independent of the size of the context. What is the dimension of WH, by the way? So let's say the dimension of the hidden state is 4. It's a vector, right? And this is also 4. So that the dimension of WH will be 4 cross 4. What is the dimension of WE? Let's say the dimension of the embedding is 10 and the dimension of hidden state is 4. So this is 10 cross 4 or whatever, 4 cross 10, right? And this is fixed irrespective of the size of the context length. It only depends on two things. One is the size of the hidden state that we'll define beforehand, and the size of the embedding that is also constant, right? Clear? Okay, so let's see how you can use RNN to predict the next word, right? So this I already mentioned. Let's say the students opened there. Okay, this is the embedding E1, E2, E3, E4, right? And this is the projection layer WE. These are the hidden states. WH is again parameter matrix, right? And so on and so forth. You can ask, what is this E? E is a embedding lookup. Embedding lookup basically says that you already have a predefined embedding, right? And you have an one-hot encoding. You multiply the one-hot encoding with the predefined encoding, and you retrieve the corresponding embedding. These are metrics, right? Or this is a vector. Okay, so then what you do, whatever things you obtain at the last layer, which is H4, corresponds to the word there, right? You pass it through a linear layer U, pass it through a linear layer followed by nonlinearity, same process, sigmoid, right? It will return a distribution, and then you sample from the distribution. Okay, so this is RNN. Advantage, it can ideally process a context size of any length, right? Doesn't depend on the context length at all, I mentioned, right? Ideally, it can capture. It can also capture things which are far from each other. Long distance relation can also be captured. But CNN, remember, CNN can't capture long distance relation. Why? Because CNN only depends on the previous few contexts, previous few words. But here, ideally, if you look at it carefully, every layer, let's say a Tth layer, has the information of all the previous layers from 0 to T minus 1 with certain changes, right? Ideally. Why ideally? I'll tell you later. Model size doesn't increase with the increase of the context length, right? And this symmetricity, right? Same weights are the same weight. If you look at this WE, this is multiplied with all the embeddings separately, right? Now this guy E1 will affect WE similarly to, right, E2 will also affect I mean the effect of E1 to WE and the effect of E2 to WE will be more or less similar. I mean similar in the sense will give fair chance to both E1 and E2. What are disadvantages? The first disadvantage is that this is slow. Why? Because this is a sequence model. To compute the hidden state at Tth time, you need to compute all the previous hidden states, right? And the second problem is that although I mentioned that it can capture long distance, right? But as the size of the context increases, we will see the effect of the first word, for example, to the last word will reduce, right? So as we increase the steps in RNN, the effect of the words which are far from the current word will be less. Okay. So now we move to the training part of RNN. Okay. So in training an RNN, we need to first look at a loss function. Consider a loss function, right? So now look at it. This diagram again. the objective is to predict the next word. Okay, in fact you assume that the objective is to predict the next word at every timestamp, right? When you are here, your objective would be to predict the next word, which is students. When you are here, your objective would be to predict the next word, which is opened. When you are here, your objective would be to predict the next word, which is there, and so on and so forth, right? You also assume that, again, just for simplicity, assume that the input vectors are one-hot encoding, okay, not embeddings obtained from glove or whatever. Okay, so here you generate a hidden state the way I mentioned earlier, right? And there is this linear layer U followed by nonlinearity. It will produce a distribution over all the vocabulary words, right? And you choose a sample from it, right? And let's say the sample is teachers. The sampled output is teachers, right? What do you mean by the sampled output is teachers? So you basically retrieve the word teacher because its probability was quite high, right? And I also know the one-hot encoding of the word teacher, right? I also know the one-hot encoding of the word students, right? So student is my ground truth, but the output I obtained here is teachers. So what is the loss? Students embedding and teachers embedding difference. How do you do this? We use cross entropy. So we'll measure a cross entropy here. Similarly, we measure a cross entropy here, cross entropy here, cross entropy here. There is a small twist here, right? When you train, let's say, ideally what should happen? Ideally, it should be something like that. If the output here is teachers, the teacher output should be fed here, right? And the model should be able to predict the next word as opened. Let's say the model predicted closed. Closed should be given here. So there are two paradigms, right? In one paradigm, whatever output you obtain, you feed that output as an input to the next layer. The other paradigm is that whatever ground truth you have, input you have, that will be your input to the layer. So if the ground truth is fed to the model, if the output is not fed, the ground truth is fed, it's called teacher's forcing. Okay? It's called teacher forcing. Remember this term. Right? So at every time, at every instance, we have this cross entropy. Let's say J1 theta, J2 theta, J3 theta, J4 theta, right? And we take the sum of all these losses, which will be my overall loss, right? Overall loss is this, and we basically take the average of it. There are t number of instances, so this will be 1 by t of total loss. Now let's look at the cross entropy a bit carefully. Cross entropy is defined by cross entropy is already I mentioned cross entropy, right, in one of the classes. So cross entropy here is basically happening between the predicted embedding and the actual embedding. Hat is the predicted one and this is the actual one. Okay, so the actual one is one-hot encoding. Okay, so it means that all zeros except only 1 1, right? So if you do position wise cross entropy, essentially you will only consider that value of y hat whose corresponding y is 1, right? So this is y and this is y hat. Y looks like this 0 0 0 1 0 0 0, something like that. Y hat is 0.5, it's a 0.3 and so on and so forth, right? So I will only consider this entry and others will be 0 because of this multiplication. So essentially this is minus log of the probability that you minus log of the entry that you generated, the probability that you generated. Okay, all right. So now this is the total loss, and we need to, and what are the parameters, by the way? What are my parameters in the RNN? What are my parameters? There are 3 parameters: WH, WE and WU. Sorry, U, whatever, U or WU. right? So now I need to do backprop. So in backprop here, what I will do, I will use a concept called backpropagation through time. It's not a normal backpropagation. Of course, the concept is the same, but this is called backpropagation through time, BPTT. Okay, let's look at BPTT. For the discussion, I will assume that there are, let's say there are H0, H1, H2, H3. There are 4 hidden states. Okay, and W is the matrix, and this is my loss. Just a simple diagram. Forget about WE, forget about U, because U and W are very easy to train. The main problem, the main culprit is W. So this is my loss. So when I need to compute this derivative of loss with respect to W, how do I compute? So here I use a concept of multivariable chain rule, right? Multivariable chain rule. What does it say? It says that, let's say you have a function f which is parameterized by x and y, and x and y, they are also a function of, let's say, p, right? If you want to take a derivative of f with respect to p, how do you do that? So this is my f, it is dependent on x and y, and x and y are dependent on p. I want to take a derivative of this with respect to this. How do you do this? df dx dx dp plus df dy dy dp, right? So this will be df dx dx dp plus df dy dy dp. This is the idea. This is the multivariable chain rule. Okay, now let's look at this network. Okay, and let's assume that let's say you want to measure this derivative dl dw. So to do that, I first need to look at the dependence. The dependence is very important. So this backpropagation happens through these directions, right? So this will be what? This will be dl dh3, right? dh3 dw. But h3 is dependent on h2, which is also a function of w, right? So this is not that straightforward. Now this you can easily do, but this is not that easy. So for that, let us look at the dependence tree, right? So this is the dependence tree. So L, this is L, okay? This is H3, okay? H3 is dependent on W, right? H3 is dependent on H2, which is dependent on W, right? H2 is dependent on H1, which is dependent on W. H1 is dependent on H0, which is dependent on W. Okay? So to compute del H3, del W, we need to look at all possible paths using multivariable chain rule, right? So how do we do that? Let's only focus on this component, okay? dH3 dW. So dH3 dW is essentially, look at this path. So this is one path to move to W. This is another path to move to W. This is another path to move to W. This is another path to move to W. So this will be dH3 dW plus dH3 dH2 dH2 dW plus dH3 dH2 dH2 dH1 dH1 dW plus dH3 dH2 dH2 dH1 dH1 dH0 dH0 dW. Okay, let's do some small changes here and there. dH dW plus dH3 dH2 dH2 dW plus, what is this one? Can I simplify this and this? dH3 dH1 dH1 dW plus, now look at this one, do dH3 H2 H2 H1 H1 H0, right? H2 H2 will cancel out, H1 H1 will cancel out, this will be dH3 dH0 dH0 dW. Okay, now let's see what is actually happening. Can we think of a generic equation out of this? Let's look at this. Let's write the entire equation in a reverse direction. This one will come first. So dH3 dH0 dH0 dW plus dH3 dH1 dH1 dW plus dH3 dH2 dH2 dW plus dH3 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 dW. This term, right? So here let's say t equals to 3, the third stage, right? Can I write it as sum of k equals to 0 to t, right? dHt dHk dHk dW, right? So this is, the actual derivation for this one. So ultimately, what is del L del W? This is del L, this is del HT. Sum of k equals to, let's make it generic, okay? So k equals to 0 to t, okay? Del HT del HK del HK del W. So this is the final formula. Okay, this is called backpropagation through time. And the other, when you take the derivative with respect to u, with respect to W, this would be straightforward, because I mean, you can also do it in a similar way, for example. Okay, now using this formula, you update the value of W. Okay, now what is actually happening here? Think about it now in a very high level. Last layer, you compute the loss, right? And that loss gets backpropagated. All and the W vectors, the W matrix will be updated. Similarly, you have another loss in the second position, right? That will also affect W. When you backpropagate, let's say here, you backpropagate through this, W will be updated. You also have a loss here, isn't it? You have a loss here, this will also be backpropagated. You have a loss here, this will also be backpropagated. So every position will affect W, and W will be updated multiple times, right? Okay, now think about it. What's the problem here? So if you look at it very carefully, this one, by the way, here the derivative is not so easy, by the way, because these are not normal derivatives. Remember, H is a vector. and ht is a vector, hk is also a vector, right? W is a matrix. Okay, you should know how to take a derivative with respect to a matrix, how to take a derivative of a vector with respect to a matrix, derivative of a vector with respect to a vector. You should thank Hugging Face and all these libraries, right? That you don't need to do all these things, you know, manually. Okay, so now let me write this one again. dl dw is, so dl dw is dl dht sum of k equals to 0 to t dht dhk dhk dw. Okay, look at this part. So what is this? Think about it. So these are hidden states. Okay, h1, h2, h3, right? Let's say h4, and so on and so forth. And you have a loss here L. Okay. So by the way, how do you compute this loss? dl dht. Let's say dl dh1. How do you compute? How do you compute dl dh1? dl dh1 is dl dh4 times dl dh4 dh3 dh3 dh2 dh2 dh1. Okay, so this with respect to this, when you take the derivative, you are multiplying multiple such derivatives. Now each of these derivatives, which looks like this, dk dhk dhk minus 1, right? Each of these derivatives is essentially a culprit. So if now, by the way, you are taking a derivative of a vector with respect to another vector, it will produce a matrix, right? So if the value of the matrix, I'll tell you what is the meaning of a value of a matrix. If the value of the matrix is low, right? If a value of a matrix is low and you keep on multiplying multiple such low valued matrix, multiple such low values, right, small values, and you have multiple steps, let's say from h1, so you start with h1 and then let's say h80. If you keep on multiplying these small values, you will see that this will be even lower and lower. Okay, what is the meaning of the small value of a matrix? You take the largest eigenvector, the value eigenvalue corresponding to the largest eigenvector, and if you see if this is less than 1, then is a small matrix. Okay, you can prove this also. So intuitively, if it's a small matrix, then we see the effect of the first hidden state, which is h1, on the loss L will be much lesser than, let's say, the effect of the last hidden state on the loss. And this is called the vanishing gradient problem. With the increasing depth of the RNN, you keep on forgetting the information that you had earlier. And if the matrix is large, eigenvalue is greater than 1, exploding gradient problem. Exploding gradient can be addressed using gradient clipping. You can at every stage you can say that, look, I don't want the value to be greater than some threshold. You can clip the gradient. And vanishing gradient, how do you address? By the way, the BPTT method I mentioned, backpropagation through time, there are multiple variations of it. There's something called truncated backpropagation, truncated BPTT. Truncated BPTT, you don't allow this to move till the end. Okay, you stop somewhere, and you decide you decide when to stop. I mean, how much you allow the gradient to propagate, to move. You don't allow it till the end. Okay. So this is about backprop. In the next class, we will discuss how we can address the vanishing gradient problem using advanced RNN methods like LSTM and GL. Okay, thank you.